Okay. Yeah, thanks so much for the introduction. So, yeah, I'm going to talk about learning with explanations. And if you've seen me giving any talk in the past, you will recognize the comic that should be showing up in a few seconds. There we go. So person A goes to a person B, asks, this is your machine learning system? And then person B answers, yep, you pour the data into this big pile of linear algebra, then you collect the answers on the other side. Then person A asks again, well, what if the answers are wrong? Person B says, well, you just stare at the pile until they start looking right. So if you're working with deep learning in applications such as natural language processing or computer vision, I would imagine that this sounds very familiar to you. And what I like about this cartoon is that I think it highlights two properties of, or two problems of current deep learning systems. A, they're not really interpretable. So if you are a machine learning researcher or PhD student or machine learning engineer, and you work with these models, right, you don't really have good insights into why something is working or why something's not working. And secondly, they are not sample efficient. So that means we really have to provide a lot of training data until they start to learn sensible things. And I would argue that we should be thinking about ways of, A, providing explanations to these models. So instead of training them from individual training data pairs, inputs X and outputs Y, we should be thinking about how could we potentially learn from natural language explanations or explanations in a formal language such as logic or also programs to make them more sample efficient, but also design an interface such that we get inspection into these models. And I'll talk about a few ways of how we imagine this to be working. So specifically in the past, we've been working on these transparent interfaces that would allow us to provide logical rules as explanations to these deep learning systems. And these deep learning systems would integrate these logical rules and provide us with proofs for predictions. So this is what I'll be covering mostly today. But we've also worked on combining neural representations with imperative programs to induce imperative programs, also providing us execution traces of predictions. We've also done work in combining what's called model-free reinforcement learning using deep neural networks with what's called model-based reinforcement learning, allowing us to not just give us predictions about the next action, but also giving us plans about what the agent thinks is a sensible trajectory of actions. And lastly, and I think that's a bit more in the future, I would be very excited to see if we can train these systems using potentially natural language explanations and also get natural language explanations out of these systems. And I'll talk at least about two data sets that we've released lately about making progress on that research front. So you might ask, okay, why is this important? I should also say at this point, all the work that I'm presenting today is not done at Facebook. But even before joining Facebook, we were interested in questions around fake news detection. So a question that came up in the last presidential election in the US was, what is the US employment rate in 2016? And depending on what kind of support you provide, you derive at a different answer. Right? So the support statement that you could use to answer this question could be the nation's jobless rate rose 0.2% in June to 4.9%. Right? Given that support, the answer to that question is 4.9%. But actually, if you change the support, if you, for instance, add another passage, another paragraph that mentions the percentage of persons employed in part-time for economic reasons was at 1.7%, and in April, 0.5% of Americans were marginally attached to the labor force. Right? If you not take these two support statements together, you might arrive at a different answer. So I think for us, it's very hard to come up with systems that should provide a truthness score for each of these answers. But one thing I would argue we should be thinking about doing in the future is how can we design systems that not just provide an answer, but also a way of deriving this answer and showing us how the system derived this answer. And I'll get to that later in the talk. Now, you can even go further. You can say, what if we get a question that's underspecified, something like what was the US unemployment rate? Well, it depends, right? In which year? Well, let's say 2016. Okay, and then you could get another support, right? You could say, now let's define unemployment rate as the total number of hours all Americans between 16 and 68 do work, divided by the number they could work. And then if you add to that in 2016, Americans between the age of 16 and 68 could have worked 420 billion potential working hours, you arrive at yet another answer, namely 42%, right? And we can debate of whether or not that support makes sense or not, but at least now we have a way to understand how a system, or potentially also how a person, comes up with such an answer. Okay, so what I'll be talking about is an approach that we presented at NIPS 2017 called end-to-end differentiable proving, and then specifically I'll be talking about how we extended this to be able to prove with natural language texts. And then, as I mentioned, towards the end of the talk, I'll introduce two recent data sets that would allow us to learn from natural language rules and natural language explanations, both published at eMNLP and NIPS 2018. And at this point, you might say, wait. Well, wait. This sounds very familiar. So actually, yeah, in 2017, I was giving a talk about end-to-end differentiable proving. Out of curiosity, who was here 2 years ago? A few people, 2, 3. That's great. So for most of you, this is completely new. But even for the 3 of you who have already heard about this, rest assured, I'll be hopefully not spending too much time on the end-to-end differentiable proving part, but then tell you also a bit about what we did since then over the last 2 years. Okay, so the end-to-end differentiable proving, that's joint work with Sebastian Riedel from UCL. And the application we were looking into here was knowledge-based completion. So if you work with real-world knowledge bases such as Freebase, DBpedia, and Yago, you know that these databases are incomplete. Right? So we might, for instance, have a relation called place of birth in that database, but it's actually missing, that attribute is missing for 71% of the people in the Freebase database, which is kind of weird because everybody has a place of birth. And then on top of that, oftentimes we don't have common sense knowledge explicitly stated in these knowledge bases. Right? We might know that somebody is a professor at a university, but we might not have explicitly stored that that person is giving lectures at the university, although we assume that almost every professor gives also lectures at the university. So if we now query for who is giving lectures at a specific university, we might not get all relevant answers. So what automated knowledge-based completion is aiming at is finding ways to learn to complete these knowledge bases based on weak logical relationships between entities. So to give you an example, we might be interested in whether or not Melinda lives in Seattle, and based on the fact that we know Melinda is the spouse of Bill, who is a chairman of Microsoft, which is headquartered in Seattle, that should give us some indication that it's quite likely that Melinda lives in Seattle. And the way people have been approaching this problem over the past 5-6 years is using what's called neural link prediction models. So here you have a knowledge base of facts that you know are true. You represent each symbol in these facts. So the relation mother of the entity Bart and the entity Lisa using a neural representation, so a distributed dense vector. And then you have some feed-forward neural network that at the end would output whether or not that statement is true or false. And in this case, let's say we have a statement that's false, we would measure the discrepancy between our prediction, right, the score that we get for true, versus the ground truth, in this case that this fact is false, using an objective function, and we would backpropagate through this feed-forward neural network to adjust the weights of this neural network and also to adjust the distributed representations of these symbols. So as I mentioned, this is really a very popular approach in the literature. There has been lots of work really following this paradigm. But what's interesting here is that we have these fixed length vector representations of these symbols in these models, and they can do interesting things. They can, for instance, capture similarity and even semantic hierarchy of symbols. Right? So if we want to make sure that we predict for somebody who's the grandpa of someone else, that person is also the grandfather of that person, we can make sure that's the case by just moving these vectors closer and closer in distance in the vector space. So similarly, if we have two symbols, apples and oranges, and we should make similar predictions for these two symbols, we again can move these vectors closer in distance in the vector space. Right, so very similarly to how word2vec would work or GloF embeddings would work. These vector representations can be trained from raw task data, facts in the knowledge base. We don't have to do any feature engineering. This is great. And to me, most interestingly, because I like to work with language, they can also be compositional. So imagine you had a relation in your knowledge base, which is called is a film based on a novel of the same name by. You might only have very, very few training data to learn a representation of that relation. But using these neural representations, we can even come up with a compositional representation. So we could learn some recurrent neural network that feeds this, the tokens or the words in this relation name word by word to come up with a compositional representation of this relation. And I'll show later on why this is important. The problem here is that we need a lot of training data to estimate these vector representations efficiently. And to me, most interestingly, on top of that, is that we have no direct way of incorporating our domain knowledge and common sense knowledge. Right? So you might know that a grandfather is a father of a parent. There's no way for us easily to incorporate that common sense knowledge or domain knowledge into our deep learning systems. On the other hand, if we had symbols, or if we use symbols, we also run into issues, right? We have, for instance, no good way of connecting grandpa off and grandfather off unless we really write down an explicit rule that states that a grandpa is a grandfather. Specifically, it's hard to work with similarity, right? We would like to work with the fact that apples and oranges are similar or that professors are something similar to lecturers. And then we would like to be able to make these inferences based on that, right? So if apple is a fruit and apple is something similar to an orange, we would also like to predict that orange is likely a fruit. And specifically, if we only use symbols, as I mentioned, it's going to be extremely hard to work with other modalities such as language and vision. But what we gain by working on symbols is we can actually do very powerful inferences, and we even get proofs for our predictions. So in this case, we have a very tiny knowledge base that states that Abe is the father of Homer, Homer is a parent of Lisa, Homer is also a parent of Bart. A grandfather is a father of a parent. If we now ask whether Abe is the grandfather of some entity Q, we get back in this case, two predictions, Lisa and Bart, but we also get back a proof path or a proof that tells us why the model makes this prediction. Right, so this is really old school AI, and here the question is how can we somehow synthesize that with deep learning. What's also nice is if we have such a proof system, we can quite easily debug. It's quite trivial to incorporate domain knowledge. We could just add rules. And we can also ask a domain expert to change rules in the system that we came up with. So here the question is how can we combine the strengths of, I guess, old school symbolic AI with the strengths of current deep function approximators, deep learning. So what we came up with is a neural network for proving queries to a knowledge base, so that the proof success is not going to be just successful or non-successful, but it's going to be a continuous score between 0 and 1. And that score is going to be differentiable with respect to all the parameters, meaning all the representations of symbols, the vector representations of symbols in our neural network. So that will allow us to learn vector representations or neural representations of these symbols in an end-to-end way. And it will also allow us to make use of provided rules and, more importantly, also induce logical rules from data. So after we train this deep neural network, it will tell us these are the kind of rules I came up with in order to make predictions to the knowledge base. So who here knows about Prolog? Half of the people. OK, that's great. Let me give you a very brief refresher. So we have this knowledge base that I mentioned earlier. Abe is the father of Homer. Homer is a parent of Bart. And a grandfather is a father of a parent. What backward chaining in Prolog is essentially doing, it's taking a query such as, is Abe the grandfather of Bart? And it's translating that query into subqueries. Right? If I want to check whether Abe is the grandfather of Bart, given the third rule in the knowledge base, I basically have to find whether Abe is a father of some entity, and then whether that entity is a parent of Bart. So it's basically always doing these translations using the rules that you have in a knowledge base. And it will attempt this for all rules in a knowledge base, and therefore specifying a depth-first search over all possible proofs given the query and the rules in the knowledge base. And there's one very central operation in Prolog, when backward chaining. It's called unification. So assume we have the query from before. Abe is the grandfather of Bart. What we're going to do is we're going to compare that query with every left-hand side of rules in the knowledge base. Note here that also this fact that Abe is the father of Homer is called a rule, but it doesn't have a right-hand side. Right? So we're comparing the left-hand sides of the rules, including the facts, we also call them rules, with the query. And we're doing this comparison basically on a pairwise level, right? So we compare the grandfather of symbol with the father of symbol. At this point, we're already done with the proof because we know that a grandfather of and father of, they're two different symbols. It's a failure, so it means given that, or assuming that our proof so far has been successful, now it's going to be a failure. We can try the same with the second rule. So can we unify grandfather of with parent of? Again, this will be a failure because grandfather of and parent of are two different symbols. So only in the third case here we see something interesting. So this is a case where unification will be successful. We're unifying grandfather of Abe Bart with the left-hand side of the rule, meaning we compare pairwise. Is grandfather of the same symbol as grandfather of? Yes, fine. Then we move on. Now we get to a free variable in our rule. That means we're going to bind the entity Abe to that free variable x, and we also then continue to the last part of the left-hand side of the rule. We're going to unify also y to the entity Bart. So that means, given a proof that so far has been successful, our downstream state of the proof will still be a success, but we will have, in addition to that, now these variable bindings from x to Abe and y to Bart. But here's something that's really annoying. So let's say we have a slightly different query, namely, is Abe the grandpa of Bart? Again, we would get a failure because grandpa of and grandfather of, they're two different symbols. And now the idea here is quite simple. Can we replace all of these symbols using dense vector representations that we learn from data? Right? Think of this as, let's say, word2vec if you have been working on NLP. So now instead of checking for whether or not two symbols are equal, we're going to measure their distance of the respective vector representations in the vector space. Right? So now we don't have a proof success that's success or failure, but we have some continuous score between 0 and 1. So let's say so far our upstream proof state is has a proof success of 1. Now our downstream proof state will have, again, the variable bindings as before, so we keep that symbolic. But we now have a small neural network that would measure basically how similar is the grandpa of symbol to the grandfather of symbol based on the two vector representations of the grandpa of and the grandfather of. Right? And the way we calculate this similarity is by using a radial basis function kernel and by aggregating the current similarity between the two symbols that we compare with the upstream proof success that we had so far. Right? So this is aggregated using the min function. So basically, the proof success score can only go down the further we go along the proof. So let me give you a concrete example of how this neural network would look like. So we start with a proof state that doesn't have any variable bindings and a proof success of 1. And we have a query, grandpa of Abe Bart, as before. We have these dense vector representations for each of the symbols in the query. And we're going to, as in backward chaining, try to apply every rule in the knowledge base. So we're going to compare grandpa of Abe Bart with father of Abe Homer using the dense vector representations of all of these symbols. And note here that this shouldn't unify, right? I mean, it's clear for us that grandpa of and father of are two completely different things, but the neural network here would have to learn to really disambiguate between these two symbols. So it would like to, I guess, move away the grandpa of vector representation from the father of representation so that this little neural network that I depict over there provides a score that's closer to 0 than to 1. So we're also going to try the other rule and also the last rule. Here again, something interesting happens. We have applied this rule, so meaning we matched grandpa of ape Bart with the left-hand side of the rule. This gives us variable bindings of x to ape and y to Bart as before. But it also tells us there's still two atoms or two queries we have to prove, namely, is ape the father of some z? We again will recursively apply all these rules. In this case, we make sure that the third rule will lead to a failure because we have a very simple heuristic that avoids cycles in our proofs by saying we can't apply the same rule twice. But here in this case, in the next thing we would try is also apply the first rule again. This might again, in this case, give us additional variable bindings, in this case z to Homer. Then we still have one further query to prove, namely, is Homer indeed the parent of Bart? We're again trying all of these three rules. And we also do this on this right branch over here, where we would have unified father of ape z with parent of Homer Bart. Okay, so basically what you see here is a neural network that would try basically out all possible proofs up to some predefined proof depth using neural representations of the symbols, right? And using this neural unification instead of a direct symbol comparison as you would do in Prolog. So what's nice here is that all the leaf nodes that you can see here, so the 2 at the bottom left and also the 4 at the bottom right, each of them is basically representing one possible proof. And each of them has this neural network attached that will give us a score between 0 and 1. And now, as I'll show in a bit, we can define a training objective to learn all of these representations from a knowledge base, basically. Right? So it will allow us to backpropagate through this entire proof process and changing all of these vector representations so that we prove the things we should be able to prove and are not able to prove the things we should be able to prove. Another thing I want to highlight at this point is that over here we have this rule given, right? We tell the model, look, a grandfather is a father of a parent, but oftentimes we don't know what kind of rules between entities in a knowledge base should exist. And our model actually, or our framework, allows us to induce logical rules from data by simply replacing, or by providing what we call a rule template. So it's very similar to the rule that we here provide, but with the difference that we don't know between which relations this rule holds, but we assume there's some transitive relationship in the data. We call these unknown relations, let's say theta 1, theta 2, and theta 3. These are 3 vector representations that we learn just like any other vector representation of symbols in this knowledge base. And for that, nothing has to change in terms of the architecture. The only thing we did is we basically didn't provide a rule, but we only provided the structure of this rule that you see on the left. Right? So now we can still learn all of these vector representations, and at test time we can see what are the closest existing relations to these theta 1, 2, and 3, and that gives us a human interpretable rule, as I'll show in a second. Okay, so I mentioned that all of these leaf nodes encode one possible proof path. This is seen over here. Right, so on the edge, you see the number of or the different rules that have been applied to arrive at this final proof state. What we do here is we take an aggregation of all of these possible proof paths. We take the max of all of these possible proof paths, and that becomes the probability of proving a query, in this case, grandpa of ape Bart, given the knowledge base, the rules in the knowledge base, and also the parameters of the model. Again, here the parameters of the model are the dense vector representations of all of these symbols, including the 3 parameters of the rules that we would want to induce. And then we can use a training objective, as I mentioned. In this case, we use negative log likelihood with respect to a target proof success to backpropagate through that entire neural network to learn all of these parameters. All right, so it's trained end-to-end using stochastic gradient descent such that the vectors are learned so that the proof success is high for known facts and it's going to be low for negative facts. The problem here is that knowledge bases usually don't write about things that are not true, so we have to resort to a sampling approach to corrupt basically known facts to derive likely false facts. So we compare that against the state-of-the-art neural link prediction system that has been used very successfully on knowledge base completion on many different knowledge bases. It's called Complex, and for benchmark knowledge bases, we see quite consistent improvements, except for this one knowledge base called Nations. So we get state-of-the-art, or at the time we got state-of-the-art on these knowledge bases. But more importantly for us, we were afterwards able to see what kind of rules the system induces. Right? For this countries data set where you have neighboring relationships between different countries, the model would induce a rule that if a specific country is located in a specific sub-region of a continent, and that sub-region of a continent is contained or located in a continent, then the country is located in that continent. Similarly, for UMLS, which is a medical database, the model would induce that if some drug interacts with another drug, and that drug interacts with yet another drug, then the two autodrugs interact with each other. So it would induce these transitive relationships, which frankly are extremely hard to be captured by these neural link prediction models that have been used in the past. Okay, so let me talk about what we did since 2 years ago. We tried to make this approach much more scalable, because one of the problems that we have is that we so far really have been building a proof tree of all possible proofs to the knowledge base, and that becomes frankly a computational nightmare. So we're only able to apply this to quite relatively medium-sized and small knowledge bases. And the other thing, we were able not just to scale this up, but also to be able then to prove using natural language sentences. And I'll tell you how that works. So this is the figure that I showed you before. And note that in this unification operation, we basically compare a query with, as I mentioned, all the left-hand sides of rules in the knowledge base, including the facts. So if you have, let's say, 10,000 facts in your knowledge base, which would still be a quite small knowledge base, you'd have to make 10,000 vector comparisons. That might still be fine, because you can batch all of this up and do it on a GPU. But once you have, let's say, a knowledge base of 1 million facts, then this starts to become quite tricky. Right? So how can we make this more efficient? Well, one thing that we came up with is to say, given a query representation that's one point somewhere in our high-dimensional vector space, what if we could directly retrieve the k closest other vector representations in this embedding space, and only basically calculate unification scores to those? Right? So don't even look at vector representations that we would unify that would lead to a very low unification score. Let's just discard these. Right? So there's what's called a approximate nearest neighbor search method that allows us to do this extremely efficiently for basically unifying a single query with millions, potentially millions of other facts or left-hand sides of rules. So basically what this means is that we don't have to construct this full computation graph, this full neural network anymore. We can actually prune this already while we're constructing the neural network on the forward pass. Okay, so as I mentioned, this unification now uses approximate nearest neighbor search, and instead of constructing this neural network for all possible proofs, we only follow promising proofs on the forward pass, meaning on the way we construct this neural network on the forward pass. This has one caveat. It means that we don't get the exact gradient anymore. Right? So on the backward pass, since we've been pruning away all the things on the forward pass, we don't get the exact gradient of the loss function with respect to parameters in our model. This is a problem that's very prominent in, for instance, reinforcement learning. It's called an exploration-exploitation trade-off. Right? So if we prune away things that might have led to high proof successes, but that were suboptimal in early parts of proving, then we won't be able to recover them, meaning we won't be able to learn from them. But this might still work out, right? So we might get an approximate gradient, but that might still be fine in terms of generalization performance. Okay, so I mentioned we can now prove with text. So what does that mean? Well, there are data sets that explicitly test for multi-hop reasoning capability. That means you might have not just one paragraph and then a question about that one paragraph, but you might get a question where you actually have to combine information from multiple paragraphs, multiple sentences, for instance, in Wikipedia. So it's quite exciting, and it's also quite hard for all kinds of models, whether they're neural or deep learning models or not. Here is an example. We have one paragraph that states that the Big Oak Tree State Park is a state-owned nature preserve in the Mississippi portion of the Gulf Coastal Plain. The Gulf Coastal Plain extends around the Gulf of Mexico in the southern United States, and the southern United States is a region in the United States of America. So then we can get a question: is the Big Oak Tree State Park located in where? and we know, okay, that should be the United States of America. The reason we can use the framework that I described over the last half an hour is that we can turn these natural language sentences into what's called open information extraction patterns. So it means we run a named entity recognition system that tells us what are entities in these passages, and then we use these entities that we extract as, well, the entities of a knowledge base, but more importantly, we use the natural language text between these two entities as expressing the relation between these two entities, right? And then we get these triples that we can use in this end-to-end differentiable prover. Right, so and then the query we can just translate easily to something that we can prove, right? We just take, well, the entity big oak tree state park, the relation located in, and the free variable q, and then proof. So how does that look on a high level? So previously we've been using this end-to-end differentiable prover to just encode a knowledge base. Now we also encode textual patterns that come from these Wikipedia texts. So this is the red part that you see in this figure. So we get these vector representations for the entities mentioned in text, but also for this natural language text mentioned between these two entities. And we have these rule templates as before on the right-hand side of this figure. So we provide already a few rule templates that, for instance, check for symmetry, right? If a relation holds between x and y, maybe another relation holds between y and x. And also these transitive relationships, so that we can learn about this located in transitivity. So if x is located in z, z is located in y, then x should be located in y. We also noticed something in the previous approach in terms of the robustness of rule induction. So before each of these unknown predicate representations in these rules, they were all disconnected from each other. So basically what it means is that the model can induce the same rule multiple times. Here we have now something that encourages a bit to basically make better use of that high-dimensional vector space for the unknown predicates that we use in these rule templates. And the way we do this is by a attention mechanism that makes sure that we basically don't represent an unknown predicate by a fixed dimensional vector representation, but by in a way, a probability distribution over known predicates. And then the vector representation that we use for the induced predicate is a linear combination of these known predicates. So we can, again, compare this against the state of the art on these datasets that I showed before, and what we saw is that we now, again, get much better performance on these different knowledge bases in terms of link prediction performance. But more importantly, we also get dramatic speedups. So depending on how small you set the k in the approximate nearest neighbor search, you can get up to 2 orders of magnitude speedup relative to the previous version of this end-to-end differentiable prover. And then lastly, you can again look, after the model has been trained, after this deep neural network has been trained on data, you can look at the kind of rules that the model induces. Now note that here these rules not only include symbolic relations between entities, but also textual patterns, right? It would tell you that some state is located in some country if some other state is a neighboring state to that state, and that state is located in the country. Okay, so I think I have still 10 minutes, so I want to leave some room for questions towards the end, but I also want to introduce this, I think, quite exciting data set that we worked on last year, which is learning from natural language rules for conversational machine reading. So this is joint work from some people from UCL and a startup called Bloomsbury AI, where we looked at existing machine reading comprehension data sets, specifically something that's called SQuAD, which is derived from Wikipedia. So here you get a paragraph from Wikipedia, a passage from Wikipedia, and you let a Amazon Mechanical Turker to come up with a question that can be answered based on that paragraph. So for instance, here, you ask what causes precipitation to fall. The answer here would be gravity. And what we noted is that in practice, actually, when people ask questions, right, oftentimes they are completely underspecified. For instance, here, right, somebody asked, do I need to carry on paying national insurance if I'm abroad? Well, actually, that depends. It depends on the context. It depends on the legislation in this case. Right? So you only need to carry on paying national insurance if you're abroad for more than 52 weeks and you are working for an employer outside of the EEA. So it's something you can find on the UK government website. So how can we deal with these kind of questions? Well, we argue that we have to create a dialogue agent, right? Wouldn't it be great if we could take this legislation and turn it automatically into a dialogue agent that when somebody asks questions, we can figure out when we need to ask clarification questions. Right, so in this particular case, how can we turn this text on the left-hand side into a decision tree so that we then can train a dialogue agent? So specifically here, if now somebody asks, do I need to carry on paying national insurance if I'm abroad? This agent would ask, well, are you abroad for more than 52 weeks? If the answer to that is no, then the answer by the agent is no. If circumstances changes and somebody asks or answers, yes, I was abroad for more than 52 weeks, there should be another follow-up question, namely, are you working for an employer outside of the EA? If that's true, then the agent would say, yes, you have to carry on paying national insurance. But users might also already provide some context, right? They might say, actually, I've been living in Japan for the last 2 years. Then maybe some of these questions you shouldn't be asking as a follow-up question. You should be able to derive that automatically given the legislation and the context provided by the user. So what we did is create a data set called ShARC. This is, again, utilizing Amazon Mechanical Turk to come up with a data set that allows us to train such dialogue agents. And what we did is basically we came up with a heuristic to automatically extract legislation from UK government websites. And then we asked Amazon Mechanical Turkers to generate a question for this paragraph. So at this point, it's very similar to the squad setup that I mentioned earlier. Right? So again, do I need to carry on paying national insurance? Would be a question that an annotator can come up with here. But then we get into this interesting bit where we ask multiple annotators to basically come up with a question, a follow-up question, right? So to determine whether or not, given the legislation and the question by the first annotator, another annotator can already answer that question, or whether that other annotator has to come up with a follow-up question. So this is what this annotator 3 guy on the middle right is doing. And then we generate both possibilities, right? We generate a yes and a no answer, and then again present that to the next 2 annotators, so that they again have to come up with whether or not they can answer this question already, given the context of the dialogue, the original question, and the legislation. And then you can see how this game goes on and on until we basically exhaustively annotated this entire possible tree of ways this dialogue could pan out. On top of that, we then ask yet another annotator to come up with some context, some background information for the original guy who gave the question, right? So here, that annotator would say, well, I'm currently in full-time employment with a company based in Germany. Do I need to carry on paying national insurance? And then you would again have to go through this tree and let annotators realize whether or not we can skip some of these follow-up questions. So I'm running a bit of time, but I just want to say this is a very challenging data set because it involves temporal reasoning, something like I purchased the property on June 5th, 1980. Question could be, did you own it before 1982? Here, a system should automatically infer that that's the case. It also involves geographic reasoning, textual entailment, numeric reasoning, which is really hard for these deep neural networks. So it's a very challenging data set with quite a bit of data that we gathered, lots of, dialogue trees, lots of user scenarios, and also from not just UK government tax legislation, but actually 264 different domains. So why is this exciting? Well, you have multiple tasks that you can phrase on top of that data set. One is classifying whether you can, given the chat history, answer the question with yes or no, or whether you would have to pose a follow-up question. So that's a classification task. But then even more interestingly, given that we know that we have to generate a follow-up question, can we design models that would generate that follow-up question given the legislation or given the context and the history of the dialogue? And what we see here is that actually a rule-based rewrite system, at least for now, is still performing best in this case. What it's quite close to the performance of a deep neural network, this bi-directional attention model. And there's a lot of headroom, obviously, to improve these models on these data sets. So I'm going to just mention also that we did a user study where we compared whether somebody who would get these questions and would have to answer them by actually reading the legislation, whether that person is faster and better than when that person also gets this AI assistant basically to help with answering these questions. What we found is that it's using this AI chatbot, it's both quicker but also more accurate actually. So it turns out humans find it quite hard to read legislation. Okay, so this data set is online. I'll skip the last part because I want to also give you the opportunity to ask questions and would like to thank you at this point. Yeah.
Do you see this as a precursor to some sort of advanced data lake query language?
Say again?
Do you see this as a precursor to some sort of advanced data lake querying ability?
It's a great question. I think ultimately yes, because what I really like about this is that ultimately at some point we might be able to ask a knowledge base without formulating our query in a symbolic form, right? We can actually query in natural language with this system in a way. So yes, I think ultimately we should be querying such systems or such knowledge bases with natural language. Yep.
So you mentioned sample efficiency, but I didn't see.
Yeah, I didn't show that. I don't think I have a figure for that. But basically, you can do these experiments where you reduce the number of training facts in the knowledge base, and then you see how quickly a system with or without provided background rules can learn to fill up the knowledge base. And what you see is that the model with the rules is not just better at predicting facts for the knowledge base, but also does that very, very quickly, right, because it can utilize these rules.
But are you using GLOV or any of these embeddings?
Oh, we're not using, no, we don't use any pre-trained word or sentence representations, but that's something we wanted to look into for the future.
Would you consider that sample efficiency as related to that? Or?
So yeah, you can further improve sample efficiency by doing transfer learning, basically pre-training word and sentence representations from a huge textual corpus and then using them in your downstream model. But I mean, that's a very established, well-established phenomena, right? That once you pre-train word representation, sentence representation, use them in a downstream task, then usually your models for the downstream task can learn quicker and generally also oftentimes generalize better. Yeah.
One more question, please.
Yep.
Do you have a problem in that you unify opposite rules? Because normally when you learn embeddings, for example, and you're trying to compute, say, sentiment, you discover that good things and bad things live in similar contexts. Hence, it's your model ends up confusing them. And in your case, you have to be really, really precise because you don't want to say that, you know, I like fish and fish is like meat, so I must like meat. But if I hate meat, you know.
Yeah, I'm sure you can upset people, make people upset with that. Yeah. So in a way, these examples that you mentioned in terms of mapping good and bad or different colors all into the same embedding space, that happens with Word2Vec and GLOV because good and bad and also more specifically like different colors, right? They all appear in very similar contexts. Here, if in your system you would start to predict things that are wrong as right based on not being able to distinguish between good and bad, the model would pick that up, right? Because it's not just learned from the context, it's not actually at all learned from the context in which good and bad appear in text, but it's learned from how good and bad are used to provide or to predict missing facts in the knowledge base. I don't have any experiments that actually control for that and test whether that's happening, but as long as we're not, say again?
You don't see that as a problem?
I don't see that as a problem as long as we don't initialize our symbols using Word2Vec. Once we do that, right, then actually we start off with good and bad being in the same, near each other in the embedding space. That's a great question. Yep.
Do you ever get like contradictory rules when you learn rules? Like will I ever come out with something that doesn't make any sense?
Yeah, I mean you can use rules that don't make sense, but you also get basically you can calculate a confidence in the rule by measuring what's the best score you can achieve by unifying the relation in the rule on the left-hand side of the rule with all possible relations in knowledge base, right? If that score is very low, you know that rule can never really be used. So you see some nonsensical rules being induced that have a low confidence. That means they're just never really used, and they were just initialized somewhat during, maybe before training, and then not really picked up during training. Yeah. Yeah.
Not all data sources are equal. So do you have anything that lets you put confidence levels on data source, and then so you're picking up context based on data sources that you trust more than others?
Do you mean for the first part of the talk or for the last letter one? Say again? The second part. We didn't do this, but I think it's a great suggestion. So I don't have any idea how well the current systems do for like different domains. We have these 200-something different domains, but we didn't do any analysis whether UK legislation is easier than, let's say, I don't know what. Yeah, that's a great question. You should look into this. The data set is online.